Okay, so now let's look at an orthonormal set. Okay, so a set is orthonormal if it's an orthogonal set of unit vectors. Okay, so the term normal just means that the vectors are unit vectors, have length 1. Okay, so if W is a subspace spanned by such a set of this orthonormal vectors, then we call that an orthonormal basis. Okay, because we already know that if it's a set of orthogonal vectors that they're automatically linearly independent. So they would be a linearly independent set that spans the subspace, and so it's an orthonormal basis. Okay, so we want to show that this set is an orthonormal basis for R3. To be a basis, it has to span the entire space, and so if these three vectors are linearly independent or orthogonal, then they would be automatically a basis for R3. And then we just need to confirm that they're also length 1, since we're asked to show it's an orthonormal basis, not just an orthogonal basis. So 2 things to show here. 1, is the set orthogonal? So that means every distinct pair is orthogonal. So we want to show v1.v2 is 0, v1.v3, v2.v3 is 0. So we need to show all those as 0. And then we need to show that it's normal, which means that each of them has magnitude of 1. So the magnitude of v1 is 1, the magnitude of v2 will be 1, and the magnitude of v3 is 1. Okay, so 2 things. v1.v2 will be minus 3 over the square root of 66 plus 2 over the square root of 66 plus 1 over the square root of 66, which clearly is 0. v1.v3 will be minus 3 over the square root of, I'm just going to say 11 times 66, plus negative 4 over the square root of 11 times 66, plus 7 over the square root of 11 times 66, which comes out to be 0. v2.v3 will be 1 over the square root of 6 times 66, minus 8 over the square root of 6 times 66, and then plus 7 over the square root of 6 times 66, which clearly is equal to 0. So they're all orthogonal to each other. Now let's show that they're normal, have length 1. The magnitude of v1 will be the square root of 3 over the square root of 11 squared, so that'll be 9 over 11 plus 1 over the square root of 11 squared, which will be 1 over 11, plus 1 over the square root of 11 quantity squared is 1 over 11, which is square root of 11 over 11, which is square root of 1, which is 1. v2, just the sum of the squares, so it'll be 1 over 6 plus 4 over 6 plus 1 over 6, which again is just 1. 1 over 66 plus 16 over 66 plus 49 over 66, which is 1. So this does form an orthonormal basis for R3. Okay, so now this is an interesting theorem that says that if you have a matrix that has orthonormal columns, okay, so that means the columns are orthogonal and have length 1. Then it's going to be true then that U transpose times U will be equal to the identity. And it also means that if U transpose times U is the identity matrix, then we're going to have U that's an orthonormal column, has orthonormal columns. So this is an if and only if, meaning that you can read the condition both ways. If it has orthonormal columns, that will imply that U transpose times U is equal to I, or if U transpose times U transpose times U is equal to the identity, that means that'll imply then that U has orthonormal columns. Okay, so if I want to show that quickly, I'm going to let U be represented as U1, U2. I'm just going to use a simple 3 by 3 matrix. Those are the columns of U. That means U transpose will look like this: U1 transpose, U2 transpose, and U3 transpose. So if I take U transpose times U, times the vector U, okay, so I know this product will be a 3 by 3, and it'll consist of U1 transpose times U1, U1 transpose times U2, and U1 transpose times U3, and U2 transpose U1, transpose U2, U3 transpose U2, and then U3 transpose U1, U3 transpose U1, and U3 transpose U3. Now recall, this is just the dot product. A vector transpose times the vector itself is the way we defined a dot product. So since the U's are all orthogonal to each other, the only values, the U1 transpose times U1, that's just going to be U1 dotted with itself. Okay, but since the U1 is orthonormal, it has length 1. So this value will be 1. Likewise, this one, since it's the vector dotted with itself, will have length 1, and this one will have length 1. So those are the only ones that actually are dot product with themselves. The others are the dot product. This is just U1 dotted with U2, which we know is equal to 0. So anytime the two vectors are distinct, we're going to have 0, which is everywhere except down the main diagonal. Okay, so we indeed do have the identity matrix. Okay, so you can see why that might be true. Okay, so now, okay, so if you wanted to show the other way around, that if the transpose of U times the vector U is the identity, then that would mean that the matrix U has orthonormal columns. Would be, if we know that this is equal to the identity, okay, and we know that this is in this form, then we can see that U1.U1 is 0, U2.U2 would be 0, 1, and U3.U3 would be 1. So the fact that those diagonal entries are all 1, since it's equal to the identity matrix, would tell us that these are all unit vectors. Okay, and then if you look at the other entries, the fact that they're all 0 tells me U1.U2 is 0, U1.U3 is 0. All other pairs of distinct vectors is 0. So that would tell me that this is an orthogonal. The vectors are orthogonal and they're orthonormal. Okay, so now theorem 7 says that if you have a matrix with orthonormal columns, that the magnitude of ux is just the same thing as the magnitude of the x that you started with. Now what this is saying is that if we look at the transformation that takes x to a matrix U times x, so we just have that standard matrix of this transformation, that if the magnitude of the ux is the same as the magnitude of x, what that means is that we're preserving lengths. So look at the length of x before you do the transformation, and then look at it after the transformation, and they're the same. So this just says that the transformation is preserving length. Okay, so now let's say that we start with two vectors that are orthogonal. So if we look at u or x dot y, if that's 0 before you do the transformation, and then do the transformation with x and y, which would be ux and uy, this just says that ux dotted with uy will be the same as x dotted with y. So we're preserving that dot product as well, before and after we do the transformation. And this is just saying that if x dot y was 0, meaning that x and y were orthogonal before, then ux dotted with uy will also be 0. So we've got that the orthogonality is being preserved here. Okay, so that transformation is preserving both length and orthogonality. Okay, so now let's demonstrate that with an example here. I've got a matrix U here that has orthonormal columns. So the matrix here that they were talking about had orthonormal columns. So this matrix U does have orthonormal columns. So let's show that. Show U has orthonormal columns. Okay. That means that each has length 1 and they're orthogonal to each other. So let's call this U1 and U2. So let's say U1 dot U2, which will be 2 over 3 times the square root of 2 minus 2 over 3 times the square root of 2 plus 0 does give us 0. So the columns are orthogonal. And now let's just show that their magnitude is each one. So this will be the square root of 1 over 2 plus 1 over 2 plus 0 is 1. And this will be the square root of the sum of the squares of entries, 4/9 plus 4/9 plus 1/9, which is also 1. Okay, so we have that U does have orthonormal columns. Okay, so we check that. Okay, I want to show that U transpose times U is equal to the identity. Okay, so U transpose will be 1 over the square root of 2 and 2/3. Oops, I'm taking the transpose, changing the rows to columns. So there's column 1 and here's column 2. Okay, now I'm going to multiply that by U itself, which will give us a 2 by 2. So I have row 1, column 1 will be 1/2 plus 1/2 plus 0 is 1. Row 1, column 2 will be 2 over 3 times the square root of 2 minus 2 over 3 times the square root of 2 plus 0. And then row 2, column 1 will be 2 over 3 times the square root of 2 minus 2 over 3 times the square root of 2 plus 0. And then row 2, column 2, 4/9 plus 4/9 plus 1/9 is 1. So we did show that U transpose times U is equal to the identity. And now we just need to show that UX magnitude is the same as X's magnitude. So let's first find UX. Okay, so we will have a 3 by 1. So row 1 with column 1 will be 1 plus 2 is 3. And then row 2, column 1 will be 1 minus 2 is negative 1. And then row 3, column 1 will be 0 plus 1. Okay, so that's UX. So the magnitude of UX, square root of 9 plus 1 plus 1, the square root of 11. And so now let's check the magnitude of X itself. So here's the vector. Square root of 2 plus 9 is the square root of 11. So you see that the magnitude of UX is equal to the magnitude of X. And so we've confirmed that that's true as well. Okay, so we just showed that a vector U that had orthonormal columns did indeed satisfy that the magnitude of the ux was the same as the magnitude of x itself. So we were just demonstrating that. Okay, so now orthonormal sets. So these are a couple of definitions. We're still dealing with those orthonormal sets. Now we're going to look at the columns of this matrix. Definition: an orthogonal matrix. So we know what an orthogonal set of vectors is. That just means any two of them are orthogonal. An orthogonal matrix is defined to be a square invertible matrix. Okay, so it's got to be a square matrix and it has to be invertible so that the inverse is the transpose of itself. Okay, so we saw from a previous theorem that if we had U transpose times U was the identity, then that meant that the columns were orthogonal. Okay, so if you know U transpose times U, meaning that U transpose is equal to its inverse, then that means that the columns of the matrix will be orthogonal. Okay, and if it's a square matrix, then we call that an orthogonal matrix. Okay, so any square matrix that has orthonormal columns then will be an orthogonal matrix. And then a matrix that satisfies that then will also have orthonormal rows. So not only will the columns be orthonormal, length 1 and orthogonal, but the rows will also be orthogonal and length 1. Okay, so I want to see, is this matrix U an orthogonal matrix? Okay, so to show it's an orthogonal matrix, we need to show two things. One is it's a square matrix, and second, that the inverse is the transpose. Okay, but we know that's equivalent to saying that the columns are orthogonal and or orthonormal. Okay, so we had that U was orthogonal, a matrix, and that meant that U was a square matrix and the columns were orthonormal, which is equivalent to the fact that U transpose times U is equal to the identity. So now notice also, just a consequence of that is that the rows are also orthonormal. It's easy to, no, it's not quite so easy. If you check each of the row entries and take their magnitude, they will be length 1, and you'll see also that their dot product of two distinct ones will also be orthogonal. So let me just look at the last row and show you that it does have, so let's call this V1, V2, V3. The magnitude of V3, which will be the square root of 1/11 plus 1/6 plus 49 over 66. It's not as easy to check as it was the columns because of the common denominators. So we're going to have 66 as the common denominator, so that'll be 6 plus 11 plus 49. So that's 66 over 66, which is length 1. So you can check that the rows will also be orthogonal and length 1 as well when it's an orthogonal matrix. So just be careful with the definition of this. It means that it's an orthogonal matrix means that it's a square matrix whose inverse is the same thing as its transpose. And notice, you can easily get the transpose of this by, or the inverse of this matrix by just getting the transpose. So that's one of the nice advantages to having an orthogonal matrix is the transpose is just the inverse. So if I said to find the inverse of this matrix, which is a nice problem because it's a real simple answer. So find U inverse. All you have to do is show it's an orthogonal matrix. Orthogonal matrix, not a set of vectors, an orthogonal matrix. Then we know that U inverse is just the transpose, which I can just write that down. So it's 3 over the square root of 11, negative 1 over the square root of 6, and negative 1 over the square root of 66. I'm just taking the transpose of U. Okay? So you can get the inverse easily if you have that it's an orthogonal matrix. Just find its transpose.